the age of electricity, connectivity, wireless machines, and autonomous robots. So it's about time we got to know some of the newest tech and robots on the scene. Today, they're driving, diving, and swarming. They're building things up and making them crash to the ground. I'll be taking apart some tech to see what's inside, and you can harness the power of static electricity with this DIY. All that and more coming your way.
Atoms racing out of space. Get your head around it. Profound elements, what's their place? Get your head around it. Chemical explosion, gravity in motion. Get your head around it. Get your head around it.
Hello and welcome to a very techie episode of Scope. Today we're transmitting robotic, electric, computer-generated, futuristic fun to your screen. A lot of new technology relies on computer science, but computers had humble beginnings. This is an abacus, the first computer. It consists of rows of beads that can be moved to keep track of numbers. This is the hundreds row, the tens, and the ones. And you can add more rows if you want to keep track of even bigger numbers. So the number 623 would look like this, with 6 in the hundreds row, 2 in the tens, and 3 in the ones. And you count by moving the beads from left to right and adding another bead to the next row up once you make it over 9. The abacus was used around 2500 BC, and throughout history, people have come up with more and more sophisticated machines to help with calculations, like this. This is CSIRAC. It's Australia's first computer and it's the size of a whole room. CSIRO began using CSIRAC for processing data in 1949. Unlike modern computers, there's no keyboard and no screen. Pieces of paper with punched holes representing math problems were fed into the machine that would calculate the answer and output the results on hole punched paper tape. These holes were then translated into numbers using a printer. CSIRAC was not completely automated, so people had to monitor its progress and initiate different steps of the process by hand. This type of technology saved people a lot of time, but compared to the computers we have now, the computers from the 1940s and 50s seem really slow. They could do 3 additions or subtractions in 1 second, it would take them 6 seconds to do 1 multiplication, or they could do 1 division problem in 15 seconds. Imagine if today's computers took that much time, but all the hard work, clever maths and inventive engineering paid off because now computers can be found in all kinds of modern technology, even something like this.
Did you know that almost none of the ocean's depths have ever been seen with our own eyes?
But we've designed a way to explore beneath the ocean without putting a toe beneath the surface. Hi, I'm Carl, and today I'm going to be introducing you to the amazing Starbug X.
Starbug X is like a small robotic submarine that uses a combination of GPS, sonar and other sensors to cruise the ocean's depths and explore places that are just too difficult or unsafe for us humans to get to.
To do this, Starbug has 5 thrusters, which are like small boat propellers, and these are powered by 8 kilos of lithium-ion batteries here in the hull. And these can keep Starbug working for up to 8 hours underwater.
So, let's get him ready to launch. Starbug is classified as an AUV, an autonomous underwater vehicle, which means he can operate completely independently.
But to do that, first he needs a mission.
Before Starbug hits the water, we load a mission file into his system. This contains data that tells Starbug where we want him to go, what depth to maintain, and what kind of research we want him to carry out.
So today Starbug has 2 missions. 1, his sensors are going to measure the water quality in this area, and 2, we're going to take lots of photos of this section of the seafloor.
For mission 1, Starbug's 3 sensors can detect parameters such as salinity or the saltiness of the water, dissolved oxygen and water temperature. This gives us an overall picture of the water in the area. For mission 2, his bottom-facing cameras will take continuous shots that can be combined later into one high-resolution image, giving us a broad view of the seafloor. Starbug can explore to a maximum depth of 100 meters at a top speed of 2 knots, or around walking speed. Not bad for an underwater laboratory.
And once Starbug is back on deck, we can reconnect it to the laptop and download all the data and images that we've collected on the mission.
So far, Starbug has monitored water quality in Tasmanian rivers, surveyed ecosystems in Western Australian reefs, and even photographed pieces of submerged shipwrecks.
So next time we discover a new ecosystem or a creature of the deep, it could be all thanks to Starbug.
Now from some underwater tech to some tech that makes components for other tech. That's pretty techy.
If only real planes were this quick and easy to make. Well, we can't actually make a real plane out of paper, but we can do the next best thing. Hi, I'm Martin Jerg, a design engineer. I work with a company that uses 3D metal printing to manufacture items like plane parts. This is the world's largest 3D metal printer. It makes large metal components without using any tools. The process is also called additive manufacturing because the method involves adding layer upon layer of metal to slowly build the item from the bottom up. This jet plane door hinge is the largest item that we have printed and the largest aerospace component printed yet. It is made of aluminium. It weighs only 11 kilograms and is 40 centimeters tall and 80 centimeters long. While this part took a week to print, making large complex items like this would have traditionally taken months. This part is more efficient because it is lighter and results in much less waste. The process starts with CAD, or computer-aided design. We can design one-off parts or design to print thousands of components. The printer reads CAD information to print each layer. Inside here, the printer lays down a very fine layer of metal powder across the base, about 40 micron thick, about as thick as a human hair. It then directs a high-powered laser onto the metal powder bed in a very fine spot. To our eye, it looks like it's printing in a line. Each tiny dot melts the powder metal very quickly into a liquid, which then solidifies just as fast. So, the metal powder is gradually melted together into a 3D form. We print with all types of metals, including stainless steel, nickel, titanium and aluminium. After each layer, the bed lowers slightly and the process starts again with a new layer of powder, building the part up one layer at a time. Then we brush away the remaining metal powder and inside is the new component. We can reuse the powder on the next project so it doesn't go to waste. This flexible process means we can design virtually anything. From sophisticated and intricate components for aerospace, to biomedical parts, like a bone for hip replacements. We can design and control the internal structure easily too. For example, bone replacements would need to allow for some flexibility, just like real bones, and by using different lattice structures, we can control how much movement the part has. This technology is already creating new ways of making things. We just have to make sure our imaginations and designs can keep up.
Coming up, there's some new technology in the driver's seat and you can make your own static goop. Hello again! Since you're watching this, I can tell that you're up with the latest household tech. But today we're going to take that to the next level. When you switched your TV on to watch Scope today, you probably used one of these, a remote control. Whether it's a drone, a game, or a TV, remote controls make it easy to make machines perform tasks from a distance. But now it's time for us to switch on our brains and see how it works. When you press a button on your remote, the LED sends infrared light, which is invisible to the human eye, to a receiver. So let's take one apart and see what's inside. Okay, so let's take a look at the parts. So here I have the outer case, the batteries that supply power to the remote, a board containing the LED light, copper contacts, and a microchip that contains all the electrical circuits needed to operate the remote. And here are the buttons. All the buttons line up with a different contact below. So when you push a button, it touches the contact underneath, which completes a specific circuit. So when I press the on button, the circuit for that button is completed, making the LED light on the end send out pulses of infrared light to the TV's receiver. That turns it into binary, and then the microprocessor interprets that as a command and the TV turns on. All that happens in just a split second. Sometimes tech seems almost like magic. You can switch on a TV without even touching it, or drive a vehicle without even sitting in the driver's seat. Let's check that out.
If you've ever played with one of these, you'll know how using electronics and remote controls can make for a lot of fun on four wheels.
But what if you didn't need a controller at all? Hi, I'm Paulo.
And I'm Philip.
And we're here at the CSIRO Robotics Group to show you a little bit of our UGV work. UGV stands for Unmanned Ground Vehicle. Like the name suggests, it doesn't need a driver or anyone that controls to travel safely. So vehicles like this one could be part of the future of autonomous transport. We built our UGV on top of a standard electric all-purpose vehicle.
It came fitted with a 6 horsepower electric motor and has a top speed of 24 kilometers per hour. But we've had to make a few modifications. We've added our own mechanical controls to the steering wheels, brakes and throttle to create a drive-by-wire system. These are controlled by signals sent from this laptop. You could say it's the brains of the UGV.
That is a lot of hardware. But with no eyes to see the road, how does an unmanned vehicle know where to drive at all?
We give a UGV a different kind of vibe with this.
This is a 3D mapping sensor called a LiDAR. This stands for light detection and ranging. It uses a laser to scan thousands of points per second. When the laser hits a surface, the sensor measures its exact distance from the UGV. Our onboard software then uses these thousands of separate measurements to build a very precise 3D map.
The 3D mapping sensor constantly rotates, which allows the laser to scan the greatest area and collect the most data.
So the more data and the more accurate the map, the better our UGV is going to stick to its programmed path.
Once a map is built, we can input the UGV's exact route with this user interface. Today we're asking the UGV to make a journey via specific spots called waypoints. And because our UGV is an all-purpose vehicle, we don't have to stick to the roads.
But travel is unpredictable, so what happens if our UGV meets an obstacle along the way? We have fitted UGV with obstacle detection and avoidance software. It uses 4 lasers, on each corner of the vehicle, to recognize if something or someone has stepped into the vehicle's path. If the UGV detects an obstacle, it can quickly stop and then replan a way around it.
This ensures that the UGV is firstly safe for pedestrians and animals.
And second, that the journey doesn't end just because something unexpected got in the way.
We hope our research will assist in unmanned vehicles becoming widespread, transporting us, delivering our goods in the real world, safely and efficiently.
So next time you're waiting for that special delivery, it might arrive on a UGV.
Now from some hands-off transport to a hands-on DIY.
Electricity plays a vital role in making a lot of technology work. Without it, we wouldn't be able to switch on a light, turn on the computer, or even use the phone. And today we're going to experiment with what one type of electricity can do. Hi, I'm Hayley and I'm going to make jumping goop with the help of static electricity. You'll need a balloon, corn flour, and vegetable oil. When electricity moves from one place to another, it's called current electricity, but if it gathers in one place, it's called static electricity. When you rub a balloon against your hair, you'll notice the strands stick to it. That's because the rubbing gives the balloon an electric charge, while your hair develops an opposite electric charge. This causes the two to attract to one another like opposite ends of a magnet. To test this out further, we need to begin by combining our two ingredients. Add a quarter of a cup of corn flour to a bowl and mix in a quarter of a cup of vegetable oil until it creates a slimy liquid. Then we can blow up our balloon and tie off the end. Now it's time to give it some static charge. Get a spoonful of the mixture and put it up to the charged balloon. You can hold the spoon close and watch it move, or you can drip the goop and watch it jump. You can also make a stream of goop stop flowing by holding the balloon next to it. So how does this all work? Well, just like our hair, when we rubbed the balloon against the carpet, we gave the balloon extra electrons. These new electrons generate a negative static charge, while the mixture we created has a neutral charge. When an object has a negative charge, it will repel the electrons of the other objects and attract that object's protons. So thanks to this simple experiment, we can see exactly what static electricity can do.
Coming up, these robots are working together, and there's an earthquake machine giving building materials a shake. Today we're putting our brain circuits to good use, getting our heads around some cool tech. Sometimes it's fun to get your head into some tech, like virtual reality goggles. Virtual reality, or VR, can be used for gaming, sport, medical research, safety training and more. The possibilities seem endless. You use this technology to visually transport yourself into another setting or environment and interact with the virtual reality around you. NASA is using virtual reality to help train astronauts, and they're even using something called fused reality. Rather than learning to fly only in a simulator, fused reality adds virtual images to the real world you can see. This means pilots can practice difficult maneuvers like refueling in the air while actually flying and with less risk. Now, from humans working with tech to robots working with each other.
In nature, a swarm is a community made up of individuals who are working together. They can connect, interact, and achieve a common goal.
But did you know that this behavior can also be applied to robots? Hi, I'm Giancarlo, the director of the Swarm Robotics Lab at Monash.
Hi, I'm Cheryl Yu, a robotics researcher.
And today we're going to show you how.
Swarm robotics connect robots to perform functions either that individuals cannot achieve or that are performed more efficiently than individually. This is similar to how biological communities collaborate to coordinate their efforts. Think about how an ant colony builds an anthill, or how flocks of birds and schools of fish travel in the same direction. They are individuals but connected and have a communal goal.
Swarm robotics has potential to be used where it is difficult for humans to venture safely, like disaster search and rescue locations, pollution monitoring, and mine clearing.
They have a series of sensors. They connect mechanically or wirelessly when they can detect if other robots are in their sensory field. We develop algorithms which are like a set of rules that they follow when their sensors experience specific circumstances. They are called self-assembling robots because they decide without human instruction to assemble or disassemble depending on their circumstances and according to these algorithms. They can assemble into different formations in a line or a rectangular or triangular formation depending on what works best for their purpose and the variable conditions that they sense. They might need to traverse terrain that an individual robot would be unable to navigate. A larger robot can carry smaller robots over large obstacles, or perhaps a swarm can transport heavier objects that are too heavy for a single robot.
I'm studying swarm robots who self-assemble into groups to climb and clean the outside of high buildings without human intervention, because window cleaning on skyscrapers can be very risky and dangerous for humans. But swarm robots will be able to climb the building itself to clean it, avoiding the risk to humans. So we're only at the beginning of our research into what these robots can do when they work together.
But we believe these swarms will cause a real buzz in the future.
Now from robots that are climbing up buildings to a machine that's shaking them up.
Earthquakes in built-up areas can be devastating because the buildings collapse and they can have a long-term impact on cities. Hi, I'm Graham Burnett. I'm a structural test engineer or mechatronics engineer. We've built this multi-axis structural test facility, or MAST for short, here at Swinburne. Here we can put structures to a test against a simulated earthquake. The MAST is the first of its kind in Australia. The walls and floor are 1 metre thick and able to withstand enormous pressure. The MAST facility is large enough so that we can test actual building structures like beams, columns, walls, lift wells and bridge piers. The test specimens can be 3 metres wide and 3 metres high. Earthquakes can cause buildings to shift, which along with forces like gravity and inertia can cause them to vibrate, which can cause a collapse. So we test what effect these movements can have on structures and materials. Once a test item is bolted or clamped to the crosshead and to the floor, with controlled hydraulics push and pull the arms of the crosshead to apply loads to the specimen. We test not only what the structures will withstand, but we can also increase the intensity to levels that actually cause collapse, as it is important for us to know the limits of the various structures. The MAST applies pressure loads and displacements in 3 different directions and 3 different rotations to the test specimen. The largest force that can be applied is the equivalent to the weight of 20 semi-trailers. We take the information we got from testing these individual items and create a computer model to be able to predict the effect on the rest of the building. This process is called hybrid simulation testing because it combines both physical and modelled methods of testing. So with this research, we're finding out what building materials and methods are required to make buildings safer in an earthquake. For example, using the MAST, we found out the failure mechanisms of joints between concrete panels, which has led to improved designs that we are now testing. So hybrid testing facilities like ours can help reduce the effects of earthquakes in the future. So I better get back to it.
Speaking of buildings, today we've been building our knowledge of robotics and tech, and we've been getting up to speed with all kinds of gadgets and devices, like these. There was Starbug, the underwater robot, and a 3D printer that specialises in metal. We saw an unmanned vehicle that makes science look like magic, and there was this DIY for all you bright sparks to try yourselves. You can get the specs for all that tech and more on our website. Or why not join us next time to brush up on all the facts, figures and fascination of science, where the ordinary becomes extraordinary under the scope.